Okay, we're going to get volumes of known cross-section, baby, and the most important thing you guys can do is make three-dimensional looking drawings. And if you're horrible at drawing, don't worry about it. A bad drawing is infinitely better than no drawing. A horrible drawing is a billion times better than no drawing at all. So I need you to make drawings, even if you're a guy who's horrible at art. And also, Erica, you must put that away. Please do not be texting while I'm talking. Even worse. Okay, here we go. I'm just going to start by giving you lots of examples. And you guys are going to practice drawing these crazy things. So here comes example number 1, volumes of known cross-section. Okay. I've got a solid. Okay. It's the base is the region bounded by y equals rad x, y equals 0, and x equals 4. Okay, so the base of this solid is the region bounded by y equals rad x, etc. So I'm doing this sort of thing where you get some solid, but it turns out your base ends up being the only side that's a complete flat plane. Alrighty? So it's going to kind of, well, I can't make it do that. But. So here's the next thing. Planes perpendicular to the x-axis, cutting the solid, make squares, one of whose sides is in the xy plane. So here's what I'm trying to create, all right? First, draw your region from, let me see, y equals rad x. So here's 1, 2, 3, 4. So 0, here's 1, 2, okay. Here's y equals rad x. Here's x equals 4. And here's y equals 0. So are you okay that this shape here, the region bounded by y equals rad x, y equals rad x equals 4 and y equals 0 is the base of my solid. Now, I'm going to cut my solid with squares, or rather with planes, and those planes are going to cut in such a way that one side of the square is going to reside in this region. So we're going to do this sort of thing. Whoops. And I'm going to make several representative squares. These are like wafers. So it's kind of, that should be dotted as well. Okay. All right. And so then, do you see this far point here? I can actually like connect them. So if you get the sense that this is a solid But the solid starts off fat and gets thinner and thinner until finally it comes to a point at the origin. And I can't really use this because this isn't the right formula, you know. But anyway, it's this idea that the squares start big and get smaller and smaller until you get to the origin. It's important to draw these little wafers, these representative wafers, because that ends up being what you're integrating. You're adding up all of the wafers. Let me show you how this works out. Looking at this wafer, are you okay that the thickness of the wafer is dx? Each thick layer has a thickness of dx. These are infinitesimally thin wafers. If the wafers were horizontal, if the wafers were looking like this, you know, where they're getting bigger or something as I go, you know. If this is what the wafers look like, then the thickness of each wafer would be dy. But these aren't horizontal wafers, these are vertical wafers. So the thickness of each wafer is dx. Let's get the height of each wafer. Are you okay that the height of each wafer is the y-coordinate on the curve? The y-coordinate on this curve ends up being the height of each wafer, right? Any wafer I care to choose, the height is going to be y. And because these wafers are squares, if the height is y, then the depth is y as well. So now I can get an expression for the volume of a representative wafer, the volume of any of these wafers. The volume of a wafer, we're going to call the volume of a wafer dV. That is a differential volume, one little slice of volume that you end up having to add up. You got to add up all these wafers, and the volume of one wafer is dV. And in this case, the volume of the wafer is y squared dx, length times width times height, y times dx. Now that I know the volume of the wafer, I can go ahead and add up all my wafers. I'm going to add up wafers from there to there, right? All my wafers are arranged vertically like this, so I've got to add up that wafer to that wafer, etc. So I'm going to be integrating from 0 to 4. So the volume, which is the integral of dV from 0 to 4, is going to be the integral from 0 to 4 of y squared dx. Are you okay about why the bounds have to be 0 to 4 instead of 0 to 2? I'd be going 0 to 2 if I was adding up horizontal wafers like these guys. But I got to go 0 to 4 because I'm adding up vertical wafers. And then there's finally one more step. I'm in dx land. My integral is in dx land. I'm doing everything with respect to x. My bounds of the integral have to be with respect to x, and my integrand has to be with respect to x. So I can't do this integral. I can't integrate y squared dx. This guy's got to be x's. Well, are you okay that this y-coordinate is following the graph y equals rad x? And so since y equals rad x, y squared is going to be x, correct? So this guy ends up being the integral from 0 to 4 of x dx. And now I can go ahead and do it. This is going to be 1/2 x squared from 0 to 4, and it gets me 8. You guys ready to do one on your own?
Where's your, oh.
That's what we're doing. That's the sort of thing we're doing. Here, try this. Example number 2. Region bounded by y equals x squared plus 1. Y equals 0, x equals 2, and x equals 0. That's the base. Cross sections are squares when cut by planes perpendicular to the x-axis. And one side of each square is in the xy plane. I'm going to make the drawing and then have you guys do the calculus. Because y equals 0 and x equals 0 are my boundaries, I'm going to be in the first quadrant. Okay. When x is 0, y is 1. When x is 1, y is 2. Y is 5, so I've got this. This is y equals x squared plus 1. And it's bounded by this, by this, and by this. So this is my area, this is my, what do you call it? Base. And now I'm going to make a 3D representation of what they want. So I'm going to make my wafers. Whoops, why do I do that? You guys could probably do a better job than me. Many of you can do a better job than me. But many of you will do a significantly worse job than me. And that's okay. Because you know what I say? A bad drawing is infinitely better than no drawing at all. So do you get a sense of what this thing is looking like? It's kind of looking like this. Well, no, it's not looking like this. I don't have any, oh, here we go. It's kind of looking like this, where you got the big square on that side and the little square on this side, and you cut it and you get your square cross sections. That's what you're getting and you'll notice it's big and it gets smaller and smaller, but this is my base. It's actually looking like that. I'd like everyone to please label the width, the height, and the depth of a representative wafer. Write down the volume of this representative wafer, and then do the integral. And let's see how many of you guys actually can get this right. We got about 4 more examples to do together. That is, I'd like everyone to please get an expression for dV. And you're going to get the expression for dV by measuring the width of each wafer, the height of each wafer, and the depth of each wafer. And remember, these are square wafers. It's going to look pretty darn similar to this, frankly. Make that drawing, and then get the differential volume. Get the volume of one representative wafer. and then use your calculator to get the integral. I don't want you taking the antiderivatives of crazy stuff. Huh. Well, that's weird. I would have expected something a little easier than that. Is anyone getting 13.733? Yay, that'd be good. Okay, several of you good. Yay. Any question or problem on this before we start doing even harder ones? The key, I have to tell you, the key to doing these problems, unfortunately for you guys who are horrible at art, is a good drawing. Because once you make a good drawing, you can get all your dimensions off the drawing. You can get height and width and depth off of your drawing, and you'll never get problems wrong if you have a good drawing. If you don't have a good drawing, of course, then your chances of getting a right answer are greatly diminished. Yes, sure. Okay, here we go. Okay. Region bounded by y equals cosecant of x and y equals sine of x equals pi over 6, and x equals pi over 2. Cross sections are squares. Planes. If planes perpendicular to x-axis cut the solid. Go ahead and find the volume. Step one, of course, is to graph that. Either use your knowledge of those graphs or just graph it on your graphic calculator. But you need something to write on a piece of paper so you can label it. Cosecant is 1 over the sine, right? keep working, but if you want, look up, your region should be that region shaded in region right there, between pi over 6 and pi over 2, bounded by cosecant x and sine x. Now make your squares, and you can have your squares, you know, you can have it be off to the right or off to the left. It's totally up to you. Something like this, I'd probably actually go off to the left. Photograph is weird. Now I gotta confess, my drawing looks absolutely horrible, but you know what? In my eyes, it's beautiful. Like if you're in love with someone, it doesn't matter what they look like, you think they're beautiful. It's the same with my drawing. I love it, it's beautiful. But somehow you've got to make a representative wafer so you can get the volume of that representative wafer and then integrate it. See if you get this good. Okay, well, I hope you're with me so far. Someone tell me, what's the length of one side of this square? What's the distance from there to there? Yes, Abigail. How many people agree with her that's a cosecant minus a sine? Okay, that's what it is. And there's no way I would have known without looking at a graph. I'm going, okay, from there to there, I'm going from the cosecant graph to the sine graph. This distance is going to be, you know, whatever this guy is, whatever x value that guy is, the length of one side of my square is that y coordinate minus that y coordinate, right? So this ends up being the cosecant of x minus the sine of x. That is the y coordinate of this guy minus the y coordinate of that guy. I hope you see that the thickness is still dx. What's that?
Everything's an x-line, you don't need to do it.
Right, yeah, now I don't have to do any switcheroo because I'm already, now I could have called this y top minus y bottom, you know, the y coordinate of the top graph minus the y coordinate of the bottom graph, but I think it's more natural for you guys to immediately go to xland and just go, hey, this is going to be the cosecant of x minus the sine of x, okay? Are you okay that since that's the length of this side, that also ends up being the depth? Cosecant of x minus sine of x ends up being the depth of each of these squares. So my differential volume is going to be cosecant x minus sine of x squared, and then the thickness is dx. And now all I got to do is get my volume. This is the easy part. Like I said, oh, you know, because I always tell my students, 90% of the problem is happening right here. The other 10% is happening here, you know? If you do this right, then you're gonna get this right. This is the integral of the cosecant of x minus sine of x quantity squared dx. And you tell me, what are the bounds of this integral gonna be?
Pi to the pi over 6 to pi over 2.
Okay? Why not 1/2 to 2? Why not along the y-axis?
They're vertical wafers.
Yeah, they're vertical wafers, or, you know, similarly or equivalently, I'm in dx land. If I'm in dx land, my bounds have to be along the x-axis. I can't have bounds along the y-axis if I'm in dx land. It never works that way. So yeah, this is going to be pi over 6 to pi over 2. And then you can get your answer. And absolutely, I don't want you taking the antiderivative of this thing. You know, what a hassle, what a huge bummer that would be. So I got parentheses, a cosecant is 1 over the sine, right? 1 over the sine of x minus sine of x, and parentheses squared, comma x, comma pi over 6, comma pi over 2. Also, make sure you're in radians mode. Wow, this is taking forever, okay. I'm in degrees mode. Oh, that was done. So I got 4,178. I wonder if it'll matter if I'm in degrees mode or radians mode. 0.377, yeah, I guess it makes a difference. 0.378. You guys okay with that? Then hey, let's do more. The more we do, the more we look at it, the better we get at it. Here we go. Okay. This is example number 4. Okay. Base is the circle x squared plus y squared equals 4. Alrighty. Planes perpendicular to the x-axis. Cut, do I want x-axis or y-axis? X-axis, cut squares. Get the volume. Okay. So what's happening now is my base is going to be the circle with radius 2. There we go. Perfect, beautiful circle. And then make your squares and go for it. And let's see what you guys get. It's going to be something that looks like this. This is a circular base, but the cross sections in this case are triangles. So if you imagine that these were all squares, that's what that would look like. Circular. Oops. Ugh. Someone just sent me a text. Probably a telemarketer. You guys ready? Because I'm kind of running out of time. Did you guys at least, how many people have drawn that? Okay, yay. Did you get an expression for dV, the differential volume? Okay, hey, let's do that. And again, I'm not going to beat around the bush. Let's just go for it. First of all, are you okay that the thickness of each one of these squares is still dx? Okay, here's the tricky part. The length of one side of the square, what are you going to call that length? What's that? What? Oh, you don't know? Okay. What is the length from there to there? Well, let me ask you this. What's the length from there to there? What would I call that?
R.
Yeah, it's y, right? But I don't want the length from there to there. I want the length from there to there. So what's it going to be from there to there?
2y.
Yeah, 2y. So there you go. 2y from there to there. And since these are squares, that makes this guy 2y. You okay with that? You see how easy it is. You don't, you know, I'll bet every single person who wasn't getting it was just making it harder than it needed to be. Hey, it's a 2y by 2y. If from there to there is y, that's 2y. So I'm going to have my differential volume being 2y squared times dx, alrighty, or 4y squared dx. And what do you suppose I'm going to substitute for y squared?
Oh, wait.
4 minus x squared.
X4 minus
Sure, y squared is equal to 4 minus x squared. So I'm going to stick that in. And there it is. This is my differential volume. Now I just get the volume by integrating. So I got 4 times 4 minus x squared dx. And what are the bounds of my integral going to be?
Negative 2 to 2.
Thank you very much, Fatima. Yeah, negative 2 to 2, because that's where I got squares, from negative 2 to 2. Now, what if I went from 0 to 2? What would I have to do to my answer? Yeah, double it, and that's fine too. So however you want to do it, I'm going to go negative 2 to 2, because sometimes when I do that double it thing, I forget to double it, and then I get only half. Alrighty, and again, you know, I mean, I know I could do this the long way, but shoot, why should I? Integral 4 times 4 minus x squared, okay, comma x, comma negative 2, comma 2, 42 2/3. Alrighty. Well, that was fun. I think I'm going to stop here. So there's some problems I need to take off of your homework. Just a second. So 1B is good. 1C, let's see if you can be clever enough to do 1C. 2B is good. 2C is diagonals.